In April 10, 1963, 220 miles east of Cape Cod, the submarine rescue ship USS Skylark receives a transmission over the underwater telephone. The voice on the other end is calm, almost too calm, experiencing minor difficulties, have positive up angle attempting to blow. Then, silence. For 15 minutes, Skylark's crew waits, straining to re-establish contact with the most advanced submarine in the United States Navy. At 0918, their sonar operators hear something they will never forget, a muted, dull thud, followed by the unmistakable roar of a steel hull collapsing under pressure. In that instant, 129 men are dead. 16 officers, 96 enlisted crew, and 17 civilian shipyard engineers, the very men who built her, riding along to watch their submarine pass its final test. This is USS Thresher, SSN 593, the lead boat of the most advanced attack submarine class the U.S. Navy had ever built. She was supposed to be untouchable. Instead, she became the worst submarine disaster in American history, and the reason every submarine that dives today does so under a completely different set of rules. By 1963, the Cold War had moved underwater. The United States and the Soviet Union were racing to build faster, quieter, deeper diving submarines, and Thresher sat at the front of that race. She was built with a teardrop-shaped hull, and HY-80 high-strength steel, engineered to dive to 1,300 feet, nearly double the depth of older American submarines. At that depth, seawater exerts over 500 pounds of pressure on every single square inch of her hull. Thresher carried the BQQ-2 sonar system, the most advanced passive sonar array ever fitted to a submarine at the time, giving her detection ranges no Soviet boat could match. She was faster, she was quieter, and she could see her enemy before her enemy ever knew she was there. The Navy was so confident in the design that it authorized construction of more than a dozen additional submarines to her exact specifications, before Thresher herself had even finished her final trials. On the morning of April 10, following a 9-month overhaul at Portsmouth Naval Shipyard, Thresher put to sea for one last test, a routine deep dive to confirm she was ready to rejoin the fleet. The dive proceeded exactly as planned. Thresher paused every 100 feet to check her systems, reporting each depth calmly to Skylark on the surface. Nothing about that morning suggested anything was wrong. That's what makes what happened next so difficult to accept. Investigators concluded the disaster began with a single pipe joint in Thresher's saltwater cooling system. Instead of being welded directly, that joint, like hundreds of others throughout the submarine, had been silver braze, a faster, cheaper method, using a lower temperature filler metal to bond the pipe instead of fusing it. At test depth, under 500 pounds of pressure per square inch, that brazed joint gave way. High-velocity seawater blasted directly into the engine room. Some acoustic analysts who later reviewed declassified sonar data argue a main electrical bus failed first, cutting power before any pipe ruptured. But whichever came first, the mechanical result was identical. Seawater sprayed across live electrical panels, triggering shorts throughout the engine room, and the reactor's safety systems responded exactly as designed. An automatic scram. The nuclear reaction shut down instantly, to prevent a meltdown. But that safety measure came with a brutal cost. Restarting a reactor takes several minutes. Thresher had none. Stripped of propulsion, taking on weight from the flooding, the crew triggered their last option, an emergency main ballast tank blow. Force high-pressure air into the ballast tanks fast enough, and you can push out enough seawater to float a 3,000-ton submarine back to the surface. It should have worked. As compressed air rushes through a valve, its temperature drops sharply, a real thermodynamic effect known as the Joule-Thomson effect. Temporary construction strainers, never removed from the high-pressure air lines, were still sitting inside those valves. The supercooled air flash froze the residual moisture trapped in that mesh, sealing the valves shut with solid ice. The ballast tanks could not empty. With no propulsion, no reactor, and a frozen blow system, Thresher continued sinking, past her structural limit, past the point of no return, until the hull gave way in a fraction of a second, 2,000 feet below the surface. Took search vessels over a year to find her. The bathyscaphe Triestia located Thresher's remains scattered across a debris field of 8,400 feet, the wreck broken into 6 major sections, spread across 33 acres of ocean floor. The investigation that followed forced the Navy into an uncomfortable admission. Post-accident testing on Thresher's own sister ship found that 14% of comparable brazed joints failed to meet basic ultrasonic inspection standards. This was never one bad weld. It was a systemic quality failure across an entire construction program, built under the intense pressure of a Cold War arms race, that left no room for the kind of scrutiny a machine like this actually needed. Less than 2 months after the sinking, the Navy established the SubSafe program, a complete overhaul of how American submarines are built, inspected, and certified. Every pipe, every weld, every valve exposed to deep-sea pressure now requires exhaustive documentation and ultrasonic testing before a submarine is ever allowed to dive. In the more than 60 years since, not a single SubSafe certified submarine has ever been lost. The only other American submarine disaster since Thresher, USS Scorpion, in 1968, involved a boat that had never been fully certified under the new standard. The 129 men aboard Thresher died in the cold dark of the North Atlantic. But the investigation into their loss rewrote the rules of submarine engineering, and every American submariner who has come home safely since has done so, in part, because of what was learned from them.